Okay, so we're continuing talking about rotational inertia, which again, that was the mass times the distance from the center of rotation, which we call the radius, squared. When we're talking about extended bodies, though, remember that extended bodies have masses concentrated in different areas. There are many different shapes that allow for this mass to be distributed differently. You're like, well, that sounds great, but there's a lot of different shapes. How can we talk about rotational inertia with all these different ways of the masses being distributed kind of throughout the shape? If you think of a bat and the way that it kind of curves out, there's more mass at the end and it's got kind of a thin handle to hold versus just like a rod. They might have the same length and even the same mass, but the mass is distributed differently. In a bat, more concentrated at the end length and the narrower versus a stick has the same mass distributed throughout. So it's actually really simple, though, to do this. We just add together. This is what this little symbol is. If you guys didn't know, that's a summation. This is called the summation of all of the rotational inertias where when we have masses distinctly concentrated at different points. We're mostly going to be looking at situations like that, as well as some special shapes. We'll talk about that later. So again, what a summation means is that the mass of the first object times the distance from center squared, plus the mass of the second object times its distance from center squared, plus the however many objects that we have. And again, when we can talk about objects, we can talk about concentrations of masses. Again, it depends on the question. We just add them all together. So it's actually really simple to do. Some shapes get a bit more complicated. Again, we'll talk about that later. So just to recall, even though we already on Friday talked about rotational inertia, we said, hey, when we're talking about speed and all of this stuff of a rotating object, we need to know rotational inertia. But we didn't really, I wanted to go back and just remind you guys what inertia even means. So remember that inertia is a measure of an object's resistance to motion. If we say an object has great inertia, that just means it's difficult to move, basically. It's going to resist motion. And again, in this case, it's based on the mass, right? And the distance from center. Both of those things increase inertia in a rotating object. In just a regular object, it's just dependent on its mass, and that's it. But with a rotating object, if we increase the mass, that will increase the inertia. Again, heavier things are more difficult to move. But if you increase the distance from center, that also increases the inertia. If you can think again, if I have a pencil here and I'm rotating it, this is pretty easy to do because the distance from center that I'm rotating this pencil is not that hard. It's not that long. Yeah. However, if I were to even keep the same mass of this, now this is very light, so it'd be difficult to do to maintain the integrity of the pencil. But if I were to extend this pencil and somehow flatten it out as if it were clay and stretch it, and then try to spin it around the center again, it would be more difficult. If you've ever done this again with spinning a stick around, the longer the stick, the harder it is to rotate. That's because it has a greater rotational inertia, resistance to motion, if we are increasing that distance from the center of the object. That's also why, again, even just rotating from the center here versus rotating from the end of the pencil, it actually is a little bit difficult, more difficult. Obviously, again, the pencil is not very heavy, so it's not going to be that much more difficult. But rotating from the center here, that distance is not very long versus if I rotate here, well, now I've doubled the distance. So it's going to be more difficult to move. It's going to have a greater inertia and a greater resistance to that motion. Let's go ahead and look at this. This is actually not too difficult to deal with here. We're just going to add together these individual inertias. So you have a barbell, which if you guys know, it's for working out. It sounds so stupid here. I'm just going to read what it says. It's made up of two small massive spheres. So there's two small massive spheres connected by a lightweight rod with a length much greater than the radii of the spheres. The reason why they specify this is because if the spheres were really close together, we'd have a very different rotational inertia. So we're saying these spheres are smaller-ish and a decent distance apart. So this is just, again, like if you're doing chest presses. I think this is what you would use. And we're calling them spheres for right now, even though sometimes they're discs. We're just going to call them spheres to make them simple. So this barbell has two identical spheres of 50 kilograms each and rotates about the midpoint of the bar. So what this is, it means, I'm going to draw a little picture here. Here's our two spheres connected by a thin, lightweight rod. We're pretending it's lightweight. Typically, again, the rod adds like another 45 pounds, I think, or however much that is in kilograms. But for the purpose of the question, and we'll talk about why later, we're going to say it's lightweight, and we can kind of ignore that. The important thing we have to realize here when we're doing this is an extended object, right? We have these two masses concentrated at the end. The important thing is to know where the center of rotation is. So this rotates about the midpoint of the bar. So go ahead and take a moment, think about where that rotation would be. So this is where, that's our center of rotation. Very important to understand that. So we want to know, what is the rotational inertia if the spheres are 1.2 meters apart? So there is some crazy bodybuilder out there who's just holding onto this barbell and like rotating it about the center, and it's just going like this. It'd be very difficult to do. And they are 1.2 meters apart. Now what that means is from the center of their masses, they are 1.2 meters apart. So technically we got a little bit of distance right here into the center of the barbell. Whenever they talk about being a distance apart, we are referencing the center of the mass to make it easier to simplify. So what we're going to do again, if here's my center of rotation, but this whole thing is 1.2, we are going to add together their individual inertias. It's going to be the summation of the mass times the radius squared. And this is going to be our answer. That's it. So we have the mass of the first barbell times its distance from the center squared, plus the mass of the second barbell times its distance from the center squared. And that's it. The only thing to be careful about is noticing the distance from center. So I want you to look at this picture and think, both of these barbells are the same distance from center, since we're spinning this barbell about a midpoint, right? The spheres are going this way. What is their distance from center? Well, it's half of 1.2, right? If the whole bar is 1.2 meters, well, this is 0.6 meters and this is 0.6 meters. So this is really the only thing we need to be careful about, is noticing again where our center of rotation is at and talking about the distance from that versus the total distance apart from these masses. So the mass of one sphere is 50 times 0.6 squared plus, hey, it's the same thing, 50 times 0.6 squared. If I chose to move this center of rotation, that would change the distances I would use. In this case, it's the same thing both times, since the masses are the same and the distance from the center is the same. So all I gotta do is plug this in. So we got 50 times 0.6 squared, oops, delete, times 2, basically. I guess I can do that. So we should get a rotational inertia of 36. Now, something I kind of left off, I'm going to go ahead and add units here because there are actually units. If you guys are ever unsure what a unit is, it's based on what we're multiplying. So since inertia is mass times radius squared, the units are the units for those things. So mass is kilograms, and the radius is measured in meters, but it's the radius squared, so it's meters squared. So it's kind of weird. Again, some concepts do not have a special unit like a Newton or a joule. Sometimes it's just based on, again, what the formula for that thing is. So we would say this is a rotational inertia of 36 kilograms times meters squared. So let's go ahead and try it one more time. This is the same situation. Oh, excuse me. Almost the same. We have made the barbell longer. So we have still 50 kilograms each, but now it's 2.4 meters. This is a really long barbell. 2.4 meters is kind of long. So we are going to now calculate the rotational inertia of the barbell if the axis has moved. The axis is located through the center of one of the spheres. So if I draw my picture here, here is my axis of rotation. And they are 2.4 meters apart. So I want you guys to try this, think it through. We are going to add together their individual rotational inertias. So we need the summation of the mass times the distance from center. I want you to think that through. This distance from the center of the rotation. What do you think this would be? Go ahead and just give it a shot. We are rotating through the center of one of the masses. Again, you can imagine this other mass swinging around the outside, and we're just spinning this one here. Go ahead and try it. Okay, well, if we look at them individually, the first ball does not have any distance from the center of rotation, because like I said, when we're talking about the distance apart, we are referencing the center of the masses. So if I'm rotating through the center of this mass, if I go to plug this in, it does not have any distance from the center of rotation. So that would be 0. And then we have the distance here being a whole 2.4 for this mass. So, oh, sorry, plus. So 50 times its distance, 2.4. So all we have is the rotational inertia of this one object. That should make a little bit of sense, because if I'm using that center object to spin something around, it's not going to matter. That one is just kind of staying in place and rotating here. Again, you can remember this from the video we watched on Friday. This is why that guy at the center of the gravitron ride just kind of sits there and is like, yeah, this is great. Because he's in the center. So he's just kind of like, the rotation is happening around him. So we have 50 times 2.4 squared. So this has a rotational inertia of 288. Again, this is kilograms times meters squared, but we don't necessarily need to know that. You can leave that off, that's fine. Okay, I want you to try one more. Oh, sorry, yes. So determine the kinetic energy of the barbell if it rotates at 1 radian per second around this new axis. So look back. We're doing the kinetic energy now. We did that formula on Friday. Look back through your notes. This is the rotational inertia. This is its angular speed. Go ahead and find it. I need to remind myself. Isn't it 1/2? Oh, crap. Okay. Okay, so looking back to our notes, the kinetic energy of this barbell then, we have 1/2 that inertia times its angular speed squared. Now, again, this is only 1 for its angular speed. And again, this is its angular speed because it's radians per second. This isn't its actual speed. So we're just going to have 1/2 times the 288 times, well, its angular speed is only 1, so it's not going to affect anything. So we have a kinetic energy really of 1/2 of 288, so 144 joules. Okay, so two last little notes we need to make here that we just need to keep in mind. Again, as I said earlier, it's really important that we identify the axis of rotation before you determine inertia. If we're looking at these different situations, it's all the same object, it's a DVD. rotating through the center versus if you like stuck a pencil or drilled a small hole through and rotated around the edge, or even having it attached to a string and rotating it here. Those are all different inertias, different rotational inertias. And so, again, it's really important to understand this distance from the center. This is a different distance, this is a different distance, and this is a different distance. So just keep that in mind. It's really important to ask yourself, how far away am I from the center? Now, the last thing here, you don't need to write these down. You just want to keep them in mind when we're looking at these questions we're going to do in the homework. There are special formulas for special types of rotations with special objects. They will be given to you in the question. But we want to just understand what it is that they're giving us if we happen to see it. Because again, the way the masses are distributed, a hoop, for example, if I were to roll a hoop versus rolling a disc versus rolling a sphere, you might say to yourself, those are all round objects. They should operate the same way. Not actually, because again, the mass is distributed differently. And again, depending on how you rotate it, so notice this is a formula for if I were to rotate it through the center versus if I drilled a hole, like if you can imagine a Pringles can, if I turn the Pringles can on its side and drilled a hole through the center and rotate it that way, it's different formulas depending on where the rotation is coming from. So again, not anything you need to have memorized at all. We just want to know that if you happen to see one of these formulas, you are going to do this for the rotational inertia instead of mass times radius squared. You're going to use the formula they give you. So we just need to keep that in mind when we do our practice.